Chapter 7 Sequential Logic Design Practices. This chapter we're talking about documentation standards. For example, state machine layout with a logic diagram. The circuit should show the layout and follow the basic structure of flip-flop, right? The flip-flop that used for state memory and next state logic F and output logic G. Okay, the element and component that perform the function of next state logic should write in the same group. For this output logic also, the element or device or logic gate, okay, should be written in the same group, okay, and if possible, all of these should be written in the same page of the paper. Okay. Furthermore, the standard about the logic symbol of flip-flop logic gate also should keep in the documentation. Furthermore, if possible, the designer should show the state machine description, okay, query. Maybe use some state output table, state diagram, or transition list. Okay. And sometimes maybe use some state machine description language such as ABL or VHDL or Verilog, something like that. And timing diagram also very important for the design. Okay, for example, this is timing diagram for the basic structure of state machine. Okay, as you know, the basic structure of state machine will be state memory by using flip-flop. Next state logic G, next state logic F and output logic G. Okay, for the timing diagram, let's start from clock. Okay, when clock tick, flip-flop will read, okay, the input of flip-flop or excitation signal, okay, to update its value or state variable. And of course, when clock tick, the input of flip-flop or excitation signal should be constant. Namely, when clock tick, okay, before clock tick with setup time and after clock tick with hold time, the input of flip-flop should be constant. And when clock tick, the flip-flop will give output with some propagation delay. Okay, this is propagation delay of flip-flop after clock tick and wait with flip-flop propagation delay. Then the output of flip-flop now is available, okay, to use for the for example for the output logic G and next state logic F. Okay, when this output updated or be available, that means input of F also update. Okay, don't forget that the output of flip-flop is one part of the input of next state logic F. And because next state logic F is a combinational circuit, so this circuit F also have some propagation delay based on number of logic gate and layer of the circuit. So after this input update, when the time of propagation delay of this combinational circuit, T combinational circuit is propagation delay of this part, then this output of F become available. So that mean after this excitation signal is available for flip-flop to use for the next state logic at the next clock tick. So that means when clock tick, now the output of F is available. So when clock tick, this flip-flop will read the data from excitation signal and update the new state with propagation delay of flip-flop, and repeat it again and again. So we should note that the frequency of clock is limited by propagation delay of flip-flop and next state logic F. For example, when clock tick at here, it need to wait for propagation delay of flip-flop and next state logic F. Then this output or excitation signal from circuit F become available. That means if the frequency of clock increase, maybe at here, it still be okay, right? Because the output of F is available at this point of time. But if the frequency of clock increase and become maybe something like this, and clock tick at here, it's not okay, right? It's not okay because the signal now is not available. There's something at this duration of time. So that means the period of clock for the maximum frequency should greater than this flip-flop propagation delay plus combinational circuit of next state logic F, and should be available before clock tick at least setup time or this relation, to make sure that the circuit will operate numbering. And the next topic is talking about switching input from switch. The basic input of the circuit is switch, right? And there are many types of switch. For example, for this one, it's called single pole single throw, and this one single pole, double throw. Okay, when switch, for example, let's consider some situation like this. Okay, let's consider. Okay, when I'm using single pole, single throw switch, connect this side to ground and connect this side to resistor and connect to constant 5 volt DC voltage and use this point as the output of the circuit. That will be the input for logic gate. Okay, now let's consider what happened if this switch open circuit. That means no current in the circuit. Okay, no current in the circuit. And assume that now there is no connection from this point. Okay, so that means voltage drop at here is 0, right? 0 volt. That means this point and this point is the same potential. So this point 5 volt, this point also 5 volt. Okay, and when closed switch, now current flow from 5 to the ground and some voltage drop. And because this point connect directly to ground, so this point become 0 volt. Okay, so that means for ideal case, when push this switch, and the output VA should be changed from 5 to 0 one time. But in practical, when this switch strike to this contact, some bouncing occur, namely we touch and then separate with a little distance and touch again and separate again. So when it's touched and the voltage at the point is 0, right? But when it's spread, even very small distance, this point become 5. That means, okay, the result is something like this. Okay, when put the switch, okay, when switch open at this position, and when push switch and touch the contact, touch together, so it's become 0. But when it's bounce or separate, even a little distance, so VA become 5 volt again, and when it touch contact together, and VA become 0 again. So when you switch one time, but there are many pulses, okay, occur at VA. So if you use this signal, for example, to count how many users push the switch, it should show one time, right? But if you use this signal, maybe detect positive edge, maybe it can detect 5 or 6. So the result is error, right? Incorrect count. So how to solve this problem? Okay, to solve this one, you need to use capacitor. For example, this one. Let's focus on this point at first, VA. Okay, and this one is very low resistance. Okay, now let's start from open circuit. At steady state, this capacitor acts as very high impedance or high resistance. You can treat this as open circuit component. That means at steady state, when this one open circuit, and this point is 5 volt, right? Okay, 5, because no current, right? No current. This open circuit, this one is open circuit, and assume this is very low current at the input of logic gate. So this point is 5 volt, okay, or almost 5 volt. And now when close the switch, close this one, so this 5 volt will the charge, electric charge from this capacitor will discharge through this 100 ohm, very low, right? Very low. So for the time constant, it's RC, right? With this path of the current. So time constant is 100 multiply 0.47 microfarad. So then it become 47 microsecond, something like this. So very short period, okay, to discharge. That means this point become 0. Okay. Yeah. So that means this point when touched, so VA change to 0 suddenly. But when bouncing occur when this contact separate from this point. So now, what happened to this one? This point will change, right, from 0 to 5. That means the charge, okay, the current will flow this. And because this very high, right, high resistance, so the time constant 10 kilo ohm multiplied 0.47 microfarad, then it become 47 millisecond, right? It take time. That means this point not become 5 suddenly, okay, but you increase slowly, and before it's greater than threshold voltage of logic low, this contact touch together again. So this point then become 0 again. So if you select this capacitor, okay, large enough, so the change at this point is very slow and always lower than threshold voltage for logic low. So it cannot become logic high. Okay, so you can solve this one. And if you want the signal become sharp, you may use this inverter. Okay, connect to this one. You change, right? High to low and low to high, something like this. Okay, and this kind of circuit is called debouncer. Okay, switch debouncer. Okay, to solve the problem of bouncing effect of the switch contact. And for the second pole diameter switch, okay, you may use this one. You may use bistable circuit. For example, if at the beginning, if it touched at this point and separate from this one. This is ground 0 volt, right? So it becomes 0 volt at here. So output maybe logic high, right? Maybe near to 5 volt. And 5 at here. So this is inverter, so it becomes 0 at here. Okay, and keep this state. And when the contact separate from this point and be between this and this, namely is in the air, this circuit is bistable, right? So it can keep this value 5 logic high and 0 logic low. And when the contact touch this point, now it becomes 0 at here, right? So it's 0 at here, so change 5 at here, then become 5 at here, and it is 0. So it change high at here, low at here. When bouncing occur, it separate, right? Separate. Then the circuit now is bistable, so it can keep the status of this point and this point. Okay. So that means the previous one, when this contact at this point, 0 at here, 5 at here, 5 at here, 0 at here. When bouncing occur, it's separate at here because it's bistable, right? So it can hold, okay, the state, namely 5 4 at here and 0 4 at here. So you can use this one for switch debouncer. Anyway, if you use this bistable circuit, some problem occur because if you start from here, right, 0 at here, 0 at here, 5 at here, 5 4 at here, right? When this contact move and touch this point, then this point become 0 volt suddenly, as this output is 5 volt, right? So it's 5 and 0, and for a short period, maybe some current flow from 5 to 0 with is quite high, okay, current, and may this device, okay, the semiconductor device may be damaged by this surge current. So to prevent this problem, we may use SLH, namely with this one. When switch is at this position, contact at this point is 0, right? So output then become 5, okay, become 5 at here. So and this is 5, right? It's 5 at here, 5 5, okay. So this output then become 0, right? 0 4 at here, okay, then 0 at here, so it is 5 at here, okay. And when this contact move, okay, and touch this one, note this point is not, okay, connect directly to this output, okay, it's not connect directly to the output of logic gate, so you can prevent, right, and the logic gate damage by the large current. Okay, this is the solution. Okay, and for this topic is talking about power reset. What is it? At first, let's consider some state machine that have some clock and reset, maybe synchronous. At first, let's consider if there is no this capacitor, and if the reset is active low, synchronous. Namely, if you want the state machine reset, so it need logic low at here, 0 at here. Okay. At the beginning, if we start from no any power supply, okay, apply to the circuit, is 0 volt at here, all is 0, and clock circuit also need power supply. If no any power supply, that means no clock at the beginning. And now what happened? What happened if apply power supply into the circuit? Yes, this point become 5, right? It become 5. Okay, clock also get some power supply, but for clock signal, it is not generate the perfect clock or square wave suddenly. It take time. It take time before become perfect square wave. So it take time. But when you apply 5 volt into the circuit, this point become 5 volt suddenly. That means when the clock signal is okay to tick, maybe this or this. When clock tick, but this signal already become high, so it cannot reset by itself. If you want, when you turn on the power of the circuit and let the circuit start at the initial state, namely this state machine maybe have some flip-flop, right? Have some flip-flop Q, maybe Q1, Q2, something like this. Okay, at the beginning you don't know, right? The initial value of flip-flop is maybe 0 or it's maybe 1. It's quite random. Okay, if you want to reset, you need to apply reset signal, but for some application, for some circuit, okay, it's better if when you apply the power and the circuit start, okay, with the initial state by itself. So how to do it? Okay, you can do by add capacitor at here. Namely, at the beginning, this point is 0, right? This point is 0, 4. Okay, when you apply the power supply here, so now this point, okay, you change to 5, 4, but it's not change 0 to 5 suddenly, but because RC, right? So it will increase slowly. Okay, the rate of change is based on the time constant of RC. Okay, if you select RC, okay, large enough, okay, it's slowly enough to make sure that when clock tick, okay, when clock at this period, when clock occur, when clock tick, and the signal still be logic low, that means now the circuit can reset, okay, by itself at the beginning when turn on the power. Okay, this kind of reset is called power on reset. Okay, automatic reset. Okay, when turn on the power. And now let's consider this one. Sometimes the user okay, want to reset, okay, manually. Maybe press this one. Okay, now if there is no capacitor at this point, what happens if clock is 1 Hertz? 1 Hertz. 1 Hertz means this clock tick and this clock tick, okay? Is 1 Hertz, right? It's 1 second, right? Okay, when clock tick, wait for 1 second, okay, for the next clock tick. Okay, if the user press, okay, press this button at this period, okay, when you press and this point becomes 0, right, that you want to reset. If you press something like this, press and release suddenly, what happened? When clock tick at here, it detect logic 1 or logic high, right? So the circuit not reset. If you want to reset, you need to keep, okay, pressing this, okay, long enough to make sure that, okay, maybe it need to keep low level at least 1 second, okay, to make sure that when clock tick, it can detect logic low at here. Okay, but some user, okay, cannot wait, right? For the normal person, maybe press and release suddenly. So to solve this problem, you may add this capacitor into the circuit. Namely, when you press this circuit, maybe you can assume the resistance of switch is very low, near to 0 ohm. Okay, that means time constant RC when you press the switch, R at here, C at here, right? So it becomes 0, very short. That means this point can change from high to low suddenly. This point, okay, can change from 5 to 0 suddenly. But when you release the switch, this point try to change, okay, from low to high, right? But when you change, you need to, okay, current will flow this one, right, with this R and C. So now time constant is changed, right, RC. If this RC product is large enough, so the voltage at this point cannot become high suddenly, right? But you grow slowly, increase slowly. So if it's slow enough, that means when clock tick, assume this is clock, when clock tick, so it tick at this point of time, that this point is still be logic low, so it can reset even you push the switch with a very short period. Okay, and for this one also given you add capacitor, and this one is for an active high reset. Okay, and the next topic is actually some IC for latches and flip-flops. IC number 74375. This one. Okay. This is latch. Okay, there is enable C. Enable C. Inside there are 1, 2, 3, 4. 4 latch, 4D latch inside, and these 2 D latch, okay, controlled by this signal, and these 2 D latch, okay, controlled by this signal, and the output have both active high and active low. Okay, this is 4, 3, 7, 5. And how about this one? And this is D flip-flop. We have got input D clock, okay, preset clear, and 2 output of active high and active low. Okay, this IC 7474, okay, contain 2 D flip-flop inside. Okay, for the same packet. Okay, one IC, okay, have got 2 D flip-flop inside, and for the one is JK flip-flop, okay, 109, and this one, okay, is 112. This one also JK flip-flop. The difference is this one active high clock, active low K. This one clock is active low, but JK is active high. And the next device is register. What is it? Okay, okay, register is collection of 2 or more D flip-flop with a common clock input, namely to store some data or some value. Obviously, we will not store just only 1 bit, right? Okay, some value. It need to store 4 bit or 8 bit or sometime 16 bit at the same time. So it need many flip-flop, okay, that you want to read the data at the same time. Okay. This collection of flip-flop, okay, that controlled by common clock. Namely, when clock tick, all flip-flop will read the data at the same time. Okay. This kind of device is called register. Register. To read the data, okay, at the same time, okay, for multiple bit input. Okay. Example. This one is 74175. Inside there are 1, 2, 3, 4. 4 D flip-flop inside, and output have got both active high and active low output. And for IC number 174, there is no active low output. Have got only active high. So inside, okay, it is you can use, okay, this up to 6 bit, okay, data, okay, stored in this IC. So inside it contains 1, 2, 3, 4, 5, 6 D flip-flops inside. And for IC number 374, this one is 8, okay, 8 bit. 1, 2, 3, 4, 5, 6, 7, 8, okay, 8 bit. It contains D flip-flop, okay, 8 D flip-flop inside, controlled by this one, clock. And this is output enable. What is it? Okay, inside this IC with this one. If you want to use the output, so it should be logic low. Apply low at here, 0 at here, output is 1. And it's 3 state buffer at here. So it's 1, right? So the signal from input, we will go to the output. But when enable is not active, namely when you apply 1 at here, it becomes 0 at here, right? So 0 at here, so the output now is become high impedance, like open circuit at the output. Okay, high impedance. Okay, it's like open circuit at the output terminal. So if you want, okay, the data from the flip-flop, okay, go to the output terminal. You need to apply logic low at here to make output enable. Okay, OE is output enable and become active. And for this IC 373, okay, it's similar to this one, but it's not flip-flop, but used D-latch, okay, instead. Okay, and it should show some other register. This one is 273, is 8-bit also, and clear. For this one is asynchronous clear. This is asynchronous clear. Namely, if you want to clear, it will clear suddenly. Need not to wait for clock tick. And for this one, have got enable. Okay, enable control signal to make flip-flop read data. Okay, this is also 8-bit. Okay, 8 flip-flop inside, but have got common enable. Okay, how does it work? Okay, consider this one. When enable is 0, is 0. Okay, and this point is 1, this point is 0. 1 at here. So this is data, right? Data from outside. Maybe this one, 8D. This data and 1, so this data, okay, is 8D at here. Okay, and this 0 at here, so it's become 0 at here. 0 or data, external data. So this external data, okay, become, okay, at this point, okay, input of D. So now when enable is 0, the data from outside, okay, can flow to the input of flip-flop. That means when clock tick, okay, the flip-flop will read the data from this. They make the same value of this external data. But if enable is 1, what happens is 0 at here, 1 at here. So 0 at here, so it becomes 0 at here. 1 at here, 1 and what? And Q, right? So it becomes Q at here. Q also is Q. So the same data will flow to the input of the flip-flop. Then when clock tick, okay, the flip-flop will read data from D, okay, with the same value of the current state. So nothing changed. Okay, this is the operation of enable signal for this IC. Okay. Okay. The next topic is counter. Counter, what is it? Okay, it's counting circuit. Okay. Counter, okay, is a clock. Okay, synchronous state machine or clock circuit. Okay, that state diagram contain a single cycle like this. When clock tick change from S1 to S2, when clock tick change S2 to S3, when clock tick change S3 to S4, and so on. Okay, maybe it's become SM, and when clock tick, okay, it's change back to S1 again. Okay, and the state machine that contain single cycle is called counter. And if it contains M state, maybe it's called a modulo M counter, or divided by M counter. Okay, M is number of state of the counter. So, for example, for binary counter, it will count with this sequence. Maybe for 4-bit, 00, when clock tick it change to 001, when clock tick change to 0010, when clock tick change to 0011, okay, and so on. So for every clock tick, the value will increase with 1. Okay, this is binary counter. And for this example, for 4-bit, we count from 0 to 15, right, in decimal, or 000 to 1111 in binary. How many states? 16 states, right? 16 states. So it's called modulo 16 counter. Okay. And now, if I want to design counter, okay, what should I do? Okay, you should use the previous chapter for state machine design. Okay, we write the state output table or state diagram for the beginning of the design, or you can observe the behavior. For example, LSB. When clock tick, it change 0 to 1. When clock tick, it change 1 to 0. When clock tick, change 0 to 1. Note, it change 0 to 1, 1, 0. It's toggle, right? It's toggle. Okay? Toggle every clock tick. Okay? It's toggle for every clock tick. Okay? We change 0 to 1, 1 to 0. And how about this digit? For this digit, 1, 2, change, 1, 2, change, 1, 2, change, right? It change for every 2 clock tick. Okay? It toggle for every 2 clock tick. How about this one? 1, 2, 3, 4. Change 1, 2, 3, 4, right? It's toggle for every 4 clock ticks. Okay? And so on. Now to design. So you just find out the condition when the digit will toggle. Okay? Just find the condition. And because you want to design a counter circuit, that means you have no counter circuit now. So you cannot use to count 1, 2 or not, or 1, 2, 3, 4 or not, right? You have no counter circuit now. You want to design the counter circuit now. So you must observe something for the behavior of counting circuit. The first one, if you consider any digit, for example, the digit, consider when the digit will change or toggle. When? when if you observe this one, if the lower digit become 1 1 when clock tick, okay, this bit will change 0 to 1 or 1 to 0, right? Because when clock tick, it will increase value by 1, right? And when this is 1 1, that means when you add 1, so carry out occur, right? 1 carry out occur. That means this carry in, okay, add this number. If this number is 0, so it go to 1. And if this is 1, then it becomes 0 because of this is the first, okay, observation. Or you may observe that you consider this one when this digit will be toggle. It's called toggle when the previous digit, okay, change from 1 to 0. If this change from 1 to 0, the next digit will be toggle, right? 0 to 0 not change, 0 to 1 not change, 1 to 1 not change, but when 1 to 0 it change, right? This one also 0 to 0 not change, 0 to 1 not change, 1 to 1 not change, but from 1 to 0 okay, it change, right? So you can observe this one. Why? Because when this one is change 0 to 1, that means when you add 1, right? Change 0 to 1 to 0, that means carry out occur. Then this the carry out of this digit become carry in for the next digit. So if digit is 0, when add carry out, so it's become 1. If the digit, okay, is 1, then when add carry in, okay, from carry out of the previous digit, we change 1 to 0. Okay, this is also can use for design the counter circuit. Okay, let's consider this one. For this one, we use T flip-flop. Do you remember? For T flip-flop, when clock tick, the toggle occur for the output. So for LSB, it's very easy, right? You connect clock, okay, directly to flip-flop, to T flip-flop. So for clock tick, okay, it's toggle, right? Change 1 to 0 when clock tick, change 0 to 1. Okay, for every clock tick, this is LSB. Okay, follow this observation. Okay, for LSB, toggle for every clock tick. And how about the next digit? For the next digit, let me use this observation on this property. When this digit is changed from 1 to 0, the next digit will toggle. If the digit change 1 to 0, the next digit will toggle. 1 to 0 is what? High to low, right? Or negative edge. Okay, if we use, okay, this one to tick this one, we need negative edge, right, to tick this one. But for flip-flop itself, it's active high, so you need to invert, right? Change high to low, change low to high, so you can change negative edge to positive edge. So we use this active low output tick clock of the next T flip-flop. Okay, so the result is this one. For LSD, it's toggle for every clock tick. Change low to high, change high to low for every clock tick. Okay. And this one for Q1, the toggle will occur when Q0 change from high to low, right? Change from 1 to 0. So when I invert this one, it's Q0 prime, right? When Q0 change from high to low, Q0 prime is low to high. So we use this one, tick, okay, clock of the next digit. So when invert, okay, Q0 active low. So for Q0 change from low to high, Q1 toggle. Change from low to high, Q1 toggle. Okay, and so on. For Q2 also, okay, it's what playing, okay, or toggle when Q1 change from high to low. So when you use this active low output, okay, so it becomes positive edge, okay, at here. Oh, now Q2, okay, when Q1 change from high to low, because we use invert of Q1, okay, as clock tick for this flip-flop. Okay, for Q3 also, it will change when Q2 change from high to low. So when you invert, okay, we use positive edge, okay, from low to high, tick this T flip-flop. So then you can get, okay, the signal Q3 by this one. Note for the frequency of the signal, clock, right? For the clock, right? Q0, the frequency is half of clock frequency, right? Right? Namely, for the one period of Q0 or LSB, okay, is cover 1, 2, okay, 2 periods of clock. And for Q1, okay, the frequency is half, okay, it's half of Q0. Okay, period is longer than Q0. Okay, 2 period of Q0. Okay, equal to 1 period of Q1. That means the frequency of Q1 is 2 times of Q0. And frequency of Q2 is 2 times of, sorry, it's half, sorry, not 2 times. Period is 2 times, but frequency is half. Okay, frequency of Q2 is half, okay, of frequency of Q1. Frequency of Q1 is half of frequency of Q0, and frequency of Q0 is half of clock frequency. Okay, and this kind of flip-flop, okay, sorry, this kind of counter is called ribbon counter or asynchronous counter. Why asynchronous? Because, okay, this bit, okay, is use different clock signal. Namely, this one is used clock from this directly, right? But this one use this one, this used from this, and this used from this. That means when this clock tick, it is much wait for some propagation delay, right? Before the signal available, then tick this one. Okay. That means clock, okay, tick each flip-flop with different time, so it's asynchronous. For synchronous counter, it will use the same clock tick at the flip-flop for every bit at the same time. Maybe this one or this one. Okay, this kind of counter is called synchronous counter. Okay, clock tick at the same time. And for this one, we use the property of counter is when we consider, for example, this digit, you toggle when the previous digit is 1 1. Is 1 1. So if it is 1 1, when clock tick, okay, this bit will toggle. So from this one to this one, there are two configurations. For this one, it's called serial counter, and even is parallel. What different? It means parallel. Okay, let's consider this one at first. For this one, we use T flip-flop with enable. Namely, toggle will be occur when enable signal is 1, right? And when this output will be 1, because of AND gate, right? The output will be 1 when this input is 1 1 1. Okay. It's from what? It's from Q2, from Q1, and Q0. Okay, and counter enable. That means this enable will be 1 when Q2, Q1, Q0 is 1 1 1. Right? To make this bit toggle when clock tick. How about this one? This output is 1 when what? When Q1 is 1, when Q0 is 1, and enable is 1. Okay, the previous digit is 1 1. To make this bit toggle, okay, to take the value of Q2, okay, and so on. Actually, this circuit also the same idea. But to check 1 1 1, okay, this is 1 from here. To check this 1 1 is not connect to this AND gate directly, okay, but use this AND gate, okay, and use this one also with this AND gate. Okay, it's different connection. For this connection, this output, okay, connect to the next input. This output connect to the next input. So it is like a serial, okay, connection. But for this one, Q, for example, Q2, Q1, and Q0, okay, is connect directly to input of AND gate. So it's called parallel counter. It gives the same result. But for the speed, because for example, because this signal, this enable, okay, will be 1, and this input and this input must be available, right? And this input is from this output, so it needs to wait for propagation delay from this AND gate, and this one also, okay, must wait for this AND gate also. Okay, it's take time. But for this one, for parallel counter, it's connect directly, right? It's connect directly from Q2, Q1, and Q0. Okay, so it's faster than this one. Okay. just introduction for counter. Okay, for the detail and some application, okay, I will study for next lecture. Okay, see you next time.